Next talk is by Xu Wang from Colorado on electrostatic dust charging and lofting on the lunar surface.
I think we can go straight to the next slide. Thanks. So unlike Earth, the moon has no global magnetic field and air, so the entire moon is charged up. And so dust particles on the surface are charged and may be lofted or mobilized due to electrostatic force. Next slide. There have been several observations on the moon to indicate electrostatic dust lofting occurs on the lunar surface. On the left, I think you have seen this from previous speakers. That's called lunar horizon glow. That was the first evidence by Severe 5, 6, and 7 spacecraft. A recent mission by Chang'e 3 rover. So they have this rover looking at lunar rocks, and they took images and analyzed the dust deposition on the rocks. What they found is they found fine dust deposit up to about 28 centimeters high on the rocks, which is very similar height to the lunar horizon glow. And next. So here are two Apollo observations related to electrostatic dust. On the left is the LEAM experiment that detected low-speed dust at sunset and sunrise. And so that can indicate to, like a lunar horizon glow event. However, the later work by Grun and Harani found no significant rate enhancement during terminal crossings by analyzing different LEAM datasets. And also on the right, that's a sketch from Apollo 17 Commander, and showing high altitude global lunar horizon glow. You can see here on the shoulder, and also this ray pattern like high altitude streamers. The thing is caused by submicron or even nanometer sized dust particles lofted electrostatically. Again, however, later observations either by remote sensing or by in situ dust instruments didn't see that. So it's still controversy. And next slide. Beyond the moon, there have been several observations also linked to electrostatic dust transport from radio spokes in Saturn's rings, dust ponds on asteroid arrows and Comet 67P, and super smooth surface on certain icy moon Atlas. So that indicates electrostatic dust transport is a universal phenomenon on all airless bodies across the solar system. Okay, next slide. So a fundamental question is, how does dust particle obtain enough charge and to get lofted on the lunar surface in the first place? So this question remained unanswered for like decades. Next slide. So recently we had a breakthrough. We developed a new patch charge model. I think previous speaker Ben Farr has already described this. So so very simple, and we can use this little. I just want to remind you this little simple formula can help you to estimate the substantial negative charge accumulated inside the microcavities. Okay, next slide. And then we have done a series of laboratory experiments to characterize electrostatic lofted dust. Next slide. So first is the charge polarity and magnitude of lofted dust. And this chart shows the magnitude in different plasma conditions, electron beam and plasma, electron beam and UV radiation. What we found is all lofted dust particles are charged negatively, even under UV radiation. So you would think, under UV radiation, electrons will be photoemitted that will leave positive charge on dust particles. And what we found is opposite, but as I said, in the patch charge model, that agrees with the macrocavity charging, which dominates the substantial negative charge over the very top layer charge. And also the charge magnitude of what we measured is several orders magnitude higher than predicted from previous charge models, but again agrees with the pie chart model. Okay, next slide. So this is the initial launch velocity of lofted dust. On the plot shows the launch velocity as a function of dust radius. It shows a very spread distribution, and so for the same size dust particles, the launch velocity can vary a lot. We think it's because of the cohesive force. That can have a large variation because cohesive force depends on how dust particles contact with each other. But if you look at the envelope of this distribution, it does show an obvious trend. So it shows the velocity is inversely proportional to dust radius, which agrees well with the equation shown here derived from the patch charge model. Also, the dust launch velocity largely depends on dust shape. And those you see this red triangle data points taken with silicon microspheres, and their initial launch velocities are much lower than irregular shaped lunar simulant. Okay, next slide. Lofting rate, yes. So we did in the laboratory, we tried simulate the secondary emission or photo emission from lunar surface, and then we can observe the how fast dust gets lofted. And what this plot shows is lofting rate as a function of time. First, it tells us it's not a constant process. It reached the peak rate and then dies down. So the peak rate is about 5 particles per square centimeter per second. This is for about tens of micron size particles. So this is high enough to sustain the lunar horizon glow. But the average rate remained low due to this slowdown process. We think the slowdown is because the microcavities got filled up or removed due to dust movement. So that reduced the cavity charging effect. Okay, next slide. All right, these are new results we just got, and it's the size distribution of lofted dust. So we measured the size distribution between 1 micron to 40 microns in diameter. On the top, it shows the lofted dust histograms versus background. So in the bottom, we normalized the lofted dust to the background to show the true distribution, which shows basically it's a good fit. The dust size versus the distribution as the function of diameter is an exponential relationship, and showing smaller dust particles are easier to be lofted. And also this agrees with the patch charge model prediction. And the next.
5 minutes.
So now this is the unique feature on the lunar surface. They call lunar swirls, those high albedo patterns. And those high albedo patterns, they're optically immature. I think they're relatively fresh materials, which may contain pristine materials. And all those lunar swirls are co-located with crustal magnetic anomalies on the lunar surface. So there are several theories try to explain this. So one of those is electrostatic dust transport. Next slide. So this is the experiment we just have done in our lab. So this is a bed of dust. We put the tiny permanent magnets underneath the dust. If you click the movie, you will see Can I please play the movie? You will see this swirling patterns is forming by, the dust is charged by UV radiation. And what we found is dust movement is well controlled by the magnetic field. And the dust is very heavy, it's massive. They don't see magnetic field force. So what happens, we think, is the B field dictates the movement of the photoelectrons, which affect microcavity charging. So we have a expanded patch charge model, and also we did the simulation, which agrees with our theory. We have manuscript in preparation to explain this very unique process. Next. So this is the instrument that we have been developing since through 2 years. It's called Electrostatic Dust Analyzer. The idea is to put on the surface of the moon to collect electrostatic lofted dust, so we can measure charge, velocity, size, mass, and lofting rate of electrolofted dust. So the size of the instrument is about 20 cubic centimeter. It's about 5 kilos and 5 watts power. It's funded by NASA DALI program, so we're about to reach TR6 very soon, early next year. Next slide. This is how this EDA sensor works. It has 2 dust trajectory sensor units on both ends, so we can allow dust to come through either end of the instrument. Each dust trajectory sensor has 14 wires, 2 arrays. Each array has 7 wires. When charged dust comes through, so the wires will be induced charge on those wires. So then we add up those induced charges, we can get the charge of dust. And then because we have 2 arrays of wires, so the time shift between the charge signals between the 2 arrays can tell us the velocity, as shown on this charge signal plots. And then the dust particle will be deflected by this central unit called the deflection field electrodes, and then exits through another trajectory sensor. So we can reconstruct the full trajectory. And the deflection will tell us the charge to mass ratio. So then we get all the charge, velocity, and mass parameters through this instrument. All right, next. So in conclusion, I think electrostatic dust lofting is a more than 5-decade-long problem. This has been related to several lunar observations even beyond the moon. Recent lab experiments have made breakthroughs in understanding the fundamentals, charging and lofting, and their properties. So the in situ measurements now is the key to determine the ground truth of this phenomena and help us to understand surface evolution and, more importantly, human exploration on the surface of the moon. Thanks.
Thank you, Professor. And thank you for keeping us on time as well.